Okay, I want to start out with some basic integral calculations. To do that, we're going to have to talk about some summations that you may have seen before. And while we're doing that, we might as well talk about some proof by induction. So let's prove these three things. That if I add up the first n integers, I get n times n plus 1 over 2. And if I add up the first n squares, I get n times n plus 1 times 2n plus 1 over 6. And if we add up the first n cubes, we end up with n times n plus 1 over 2 squared. Okay, so let's prove these three things first. The first one I am not even going to do an induction proof on. The next two we'll do induction proofs on. But the first one's easy enough, we can just kind of do a proof by picture for that first one. So what we're going to do is I'm going to add them up in two different ways. So let's say let s equal the sum, k equals 1 to n of k, then 2s is going to equal, well, let's see how I do this. I've got 1 plus 2 plus 3 plus dot 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 plus n. That's equal to s. And here's s again. It's n plus n minus 1 plus n minus 2 plus dot 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 plus 1. So 2s is equal to n plus 1 plus, if I add these guys together, I get n plus 1. And if I add these together, I get n plus 1, and so on. And I've got n columns here, so this is n times n plus 1. So s is equal to n times n plus 1 over 2. The famous story about that one is Gauss, when he was young. Gauss is a real famous mathematician, maybe one of the most prolific mathematicians, most papers, most results due to him. When he was young, his teachers were having trouble keeping him occupied in class. He was too smart for the rest of the class. So she had enough one day and says, just go back to the classroom, into the classroom, and add up all the numbers from 1 to 1,000, and then come back and tell me what you get at the end of the day. And he walks back up to her about a minute later, not even, and he says, well, it's whatever, 50,500, or yeah, 500,500, something like that. Whatever you get when you put 1,000 into this formula, he decided, well, it's easier just to add them up twice than adding them up once. Add them up forwards and add them backwards and divide by 2. So we got 1,001 times 500, so we got 500,500, and that was his solution to that. You guys have probably seen some trouble students like that sometimes too. Okay, so let's do the next one. Let's show that the sum from k equals 1 to n of k squared is equal to n times n plus 1 times 2n plus 1 over 6. Alright. So this is going to be a proof by induction. And if you recall, induction is kind of like dominoes. You prove it for one thing, and then you prove if it was true for that, it's true for the next integer. And then you say, well, since my proof of if it's true for one integer, it's true for the next integer was arbitrary, it must be true for all integers because I started. So you knock over the first domino, show the first domino falls. And then you show that if you push over one of the dominoes anywhere in the line, the next domino will fall over, then that says that all of the dominoes are going to fall over. So our proof is going to start with the first domino falling. This is true for n equals 1, since 1 squared equals 1 equals 1 times 1 plus 1 times 2 times 1 plus 1 over 6, which is 6 over 6, right? So it's true for the first domino. Okay. So assume the statement is true for n equal to n star, some special n. We'll show it's true for n star plus 1. Stars are going to get annoying. Let me just go n hat, n tilde, n hat. Okay. So the sum of k squared from k equals 1 to n hat plus 1, that's equal to n hat plus 1 squared plus the sum from k equals 1 to n hat of k squared. And by assumption, we know what this is. By assumption, our statement is true for that summation. So this is n hat plus 1 squared plus, the statement says I've got n hat times n hat plus 1 times 2 n hat plus 1 over 6. And now I want to rewrite this so it looks like n plus 1 times n plus 2 times n plus 1 plus 1, so that I can sort of fit this together into the format of the statement. So it looks like it can factor out n hat plus 1 from the front and the back of that the summation there. So I've got n hat plus 1 times n hat plus 1 plus n hat times 2n hat plus 1 over 6. If I factor n hat plus 1 from both of those terms. Let's work with the right hand side now. So this is equal to n hat plus 1 times 6n hat, we'll put them under a common denominator, plus 6 plus 2n hat squared plus n hat all over 6. Right? Let's see if I've got my algebra right. I think I do. Okay. So that's n hat plus 1. And in here, I've got 2 n hat squared plus 7 n hat plus 6 over 6. And now we can factor. The AC method is probably how I'll factor that. I need a times c is equal to 12, so I should probably split that up into 3 and 4 in the middle. So n hat plus 1, 2n hat squared plus 3n hat plus 4n hat plus 6 over 6. And then we can factor by grouping. Got n hat times 2n hat plus 3 plus looks like a 2 times 2n hat plus 3 over 6. So this is n plus 1, and then I've got a n hat plus 2, and a 2 n hat plus 3 over 6 here, which I can rewrite as n hat plus 1, n hat plus 1 plus 1, and 2 n hat plus 1 plus 1 over 6, which is the formula applied at n hat plus 1. So we've shown that if it's true for n hat, it's true for n hat plus 1. And that shows, and by induction, it is true of all integers, at least all natural numbers. Okay. I think I'll leave the last one. I'll let you maybe guys do the last one, the cube one, as an exercise. Okay, so let's use these to integrate now. All right. So I've got squares, cubes, and just individual numbers added up. So let's try and calculate the integral from maybe 2 to 3 of x dx. Okay. The reason we had those sums is we're going to pick sort of a nice partition to break the interval from 2 to 3 into. We'll just take a partition with even width rectangles. So let p sub n, it's going to be the partition that starts at 2, and then it's going to be 2 plus 1 over n. There's n pieces in this partition. The width between 3 and 2 is 1, so if I take steps of size 1 over n, I eventually get up to 3, so this is going to be 3 minus 1 over n, and then 3. Okay, so those are my evaluation points. And we're going to try and integrate this. So the theorem that we've proven before says x is a continuous function, so it's integrable. So it doesn't matter whether I use the upper integral on the partition or the lower integral on the partition. As long as I use either one of them, they will eventually reach the same point as n gets large. So by continuity of x, we can use either u, p, and f, or I guess f is equal to x this time, or l, p, n, x, and see what happens as n approaches infinity. So let's just use the upper one. Okay, x is monotonic, so the upper one, the right hand side, is going to be the bigger point for each of these. So we're going to have u pn of x, that's going to be equal to the sum of, well, it's going to be the x sub I, because that's going to be what the maximum is, times 1 over n. Let's go with a plus 1, the maximum's on the right hand side, from I equals 0 to n minus 1. Okay, so this is equal to the sum from I equals 0 to n minus 1 of, well, let's write down what the x sub I plus 1s are, in terms of n and 2 and 3. So this is a 2 plus I plus 1 over n times 1 over n. Right, I'm starting at 0. The right hand side starts at 2 plus 1 over n. The next one is 2 plus 2 over n, 2 plus 3 over n, 2 plus 4 over n, and so on. So I get this summation here. And we can rewrite this summation. I equals 0 to n minus 1 of 2 over n plus I plus 1 over n squared. And so this is constant, it doesn't depend on n. I can pull it outside. I can say there's n times 2 over n plus 1 over n squared times the sum from I equals 0 to n minus 1 of I plus 1, which is equal to 2 plus, this was an n squared that I pulled out, 1 over n squared times the sum from I equals, well, let me change my variables. This starts at 1 and goes to n. Well, let's just say k equals 1 to n of I, of k. Okay, so this, now we can use our formula. We have 2 plus 1 over n squared times, well, the sum of k is from 1 to n is n times n plus 1 over 2. Okay, so this, let's write it out. 2 plus, here we've got n squared plus n over 2n squared. Okay, so this is equal to u of Pn comma x. And we want to see what happens as n goes to infinity, as this partition gets finer and finer. Okay, so the limit as n goes to infinity of this partition, or this integral on the partition, equals 2 plus 1/2, or 5/2. You can use L'Hopital's rule on that, or any other method you want to do to take that limit as n goes to infinity, but you're going to get 1/2 there. Okay, so let's see if that's how it works when we use our regular methods of integration, just to check ourselves, the ones that we learned in calculus. So this is going to be x squared over 2 evaluated at 2 and 3, which is going to be 9 over 2 minus 4 over 2 is 5/2. Good, that checked out for us. We actually haven't proven that this works yet, but we kind of know, because of some prior knowledge that we have, that we could use that as a check. Okay, let's do one more. Let's do the integral from 0 to x of t cubed dt, and see what this is. So this has a variable endpoint on there, but let's do the same thing with the partition. Let's take p sub n. We're going to go from 0 to x in steps of size n. So this is going to be, well, we better start at 0. X over n, 2x over n, 3x over n, and so on, up to nx over n, which is equal to x. So each of these is the same size step. Each step is size x over n. It'd take me n steps of size x over n to get from 0 to x. Alright, so u Pn of t cubed, we'll use u again. T cubed is a continuous function. We can use either the lower or the upper. We'll use, well, let's use the lower. and then we see that this is equal to the sum from k equals 0 to n minus 1. I've got x sub I, because t cubed is a monotonic function increasing from 0 to x. I've got that thing cubed times the width of one of these intervals, which is x over n. Okay, and that's going to be the sum from k equals 0 to n minus 1 of x cubed times x over n cubed, and I've got a k cubed here as well. Alright, so let's see how this works out. I've got a bunch of stuff that is fixed now. All of this part of this function is fixed. So I can pull out x to the fourth and I can pull out n to the fourth, and then I'm summing from k equals 0 to n minus 1 k cubed. Right? And that's the same thing as x to the fourth over n to the fourth, the sum from, say, I equals 1 to n of k minus 1 cubed, and I can use my formulas, or my summation formulas, on this. Alright, let me just pick the right one to write down here. So we'll still start at k equals 0, but the k equals 0 is 0, so we'll just go with this. Okay, and now we can use our summation formulas. So x to the fourth over n to the fourth times, I've got n minus 1 times n minus 1 plus 1 over 2 squared. Right? So that's x to the fourth over n to the fourth times n minus 1 times n over 2 squared. So I could rewrite that as x to the fourth over 4, and I've got n minus 1 times n over n squared, and we can take a limit as n goes to infinity of x to the fourth over 4 times this is n squared minus n over n squared. The stuff inside this parentheses, that goes to 1, so this equals x to the fourth over 4, which is what we want. So the integral from 0 to x of t cubed dt is equal to x to the fourth over 4, as we usually know.